electric transformers. Here we are going to see the principle of operation, construction and types of and applications. My name is M.Murugan, Assistant Professor in EEE Department. The learning objective of this lecture is to understand the transformer working principle and learn the construction and types, about the losses and efficiency and applications of the transformers. So actually, what is transformer? So transformer is a static device which transfers the electrical energy. Either it has to step up or step down without changing its frequency. So that's why here I am mentioning the points. It is a static electrical device and transfers the AC power. So it only transfers the AC power. Either you have to step up the value or step down the value, or whether it is increase the value or decrease the value. Then works under the principle of mutual induction. So we will see the mutual inductions one by one, and the frequency remains constant. So here we are using the AC supply. That's why we have the frequency value. So without changing the frequency value, we have to change the voltage level in the transformer. Either it is step up or step down. So here we are having the transformer. So this is the transformer core actually. This is the transformer core and this is the primary winding. So this is called primary winding and this is called secondary winding. So when I am giving the supply to this primary winding, when the current flowing through the conductor, the magnetic fluxes creates, the magnetic flux lines creates. That flux is links through this material, the core, transformer core material, and to the secondary coil. So in this coil, by means of the Faraday law, it creates, when the flux is cuts the electric conductor, it creates a voltage value. Thereby we can get the voltage at the secondary for the use. So why transformer is necessary? So why it is needed actually? First thing is voltage level matching. Suppose I am having a motor. In that motor, I have to give the 230 volt AC supply. For example, I am saying 230 volt AC supply. But in my electricity board gives only the 200 volt. Some voltage dip may occurs at the electricity side. It gives only the 200 volt supply. So at that time, I am using the step up or step down transformer, means I have to stabilize my voltage. That is the voltage level matching. First thing. The second thing is reduce the transmission line losses. It reduces the transmission line. How I can say the transmission line loss is reduced? Suppose I am passing the 230 volt AC from the sending end, means the power station, generating station. So in the generating station, I am sending the 230 volt AC supply. May or may not I can get the 230 volt AC. So the 230 volt AC gets lost due to the line resistances. Sometimes I can only get the 150 volt. My ultimate aim is to get the 230 volt AC supply, but here I am getting only 150 volt. So the generation is entirely gets lost. So in order to avoid that one, I am using the step up transformer at the power station, power generating station, and the step down transformer at the consumer side. Then only I can get the stable voltage. then the safe utilization of power. Suppose I do wrong in my electrical circuit, in my side, in our side, we did some wrong electrical connection. So what will happen if I do wrong? The short circuit may occur. If I am directly connect this line to the generating station, what will happen? The generating station also gets affected by means of the short circuit provided in the receiving end at the consumer side. So in order to isolate that the circuit, mainly we are using the transformer. So here the simplest way of explaining the transformer usage. So here we are having the power generating station. From the power generating station, I am giving the step up transformer. So if I am generating, for example, I am saying if I am generating the 230 volt AC, I am converting the 230 volt AC into some 11 kilovolt. That 11 kilovolts voltage passes through this transmission line wherever we need. Then I have to reduce to my level by means of the step down transformer. From the step down transformer, I have reduced the voltage and I can use wherever I need. So this is the simplest map of the transformer need. Then what are the basic parts of the transformer? We are having primary winding, secondary winding, magnetic core and insulation. So these are the major part in the transformer. So only we are having the primary winding, secondary winding, magnetic core and the insulation. This is the primary part. This is the primary part. Some additional things is also there according to the usage of the transformer that we will see one by one. So this is the basic parts. So this is the three-dimensional view of the transformer. So this is actually the transformer core. This is the transformer core, inside core. Here I am having the winding. So inside the core, this is the core actually. On the core I am having the primary winding as well as the secondary winding at the other end. Okay, so this is a shell type transformer. So types of transformer is coming there in the later slides. Here for explanation I am saying this is a shell type transformer. So in the shell type transformer, primary winding and secondary winding are wound in the same loop. So for the three-phase transformer, I have to wound three legs, so three limb. Here is the limb. So each and every limb has its own primary winding, secondary winding for the each phases, each three phases. Okay, so this is the transformer core, and this is the transformer oil tank. This is the oil tank. Why we are having the oil tank here? In order to cool this transformer winding. When we pass the current, it will get heated. So in order to reduce the temperature of the coil, I have to make some cooling arrangement. Here I am using the transformer oil. So in order to have the transformer oil in a container, here I am using the oil tank. Transformer oil tank. It's the outer cover. Here this is the cooling fins. So when the winding is heated up, the oil also gets heated up. In order to transfer the oil heat to the atmosphere, here I am using the cooling fins. So oil is circulated through the fins and the heat is transferred from oil to the atmosphere here. Then and there the heat is reduced. And here is the terminals of the transformer, for only one for primary and one for secondary, and these are the bushings called insulator. Okay, so generally we can call it as insulator. In the transformer set, this is a bushing, and this is called conservator. So the conservator is mainly used to maintain the oil level in the tank. So this conservator is mainly used to maintain the oil level in the tank. So these are all the parts we are having in the transformer. Then what is the working principle? Earlier I am saying that by means of the mutual induction it will work. So what is mutual induction actually? Suppose I am having the coil. If I pass the current, what will happen? Around the conductor I am having the flux lines. So if I pass the current to the conductor, we are having the flux lines around the conductor. That is the nature. So if I pass the DC current, it will give the constant magnetic field around the conductor. When I pass the DC current, keep note on it. If I pass the DC current, it will create the constant magnetic field around the conductor. So nothing happens. Suppose I am giving the DC current. Some constant magnetic field is created. That constant magnetic field is linked with this coil. But our ultimate aim is to get the voltage at this secondary coil. We have to get the voltage in the secondary coil. For that, what I have to do? I have to change the flux values, linking flux values. I have to change the linking flux values. What is Faraday law says? Whenever the current carrying conductor cuts the flux line or flux cuts the current carrying conductor, an EMF will be induced. That EMF is directly proportional to the rate of change of flux linkage. That is the main thing. So when I am changing the flux linkages in the coil only, I can get the voltage at the secondary. Here how it is happening? The AC supply having its nature to change the value each and every time, since we are called as the alternating current. So what the alternating current does? Each and every time it changes its magnitude. Each and every time it changes its magnitude. So if the magnitudes of the conductor or voltage changes, means accordingly the current values also changes, and in turn the magnetic flux lines values also gets changed. So if the rate of change of flux occurs, automatically the change of flux links with this coil, in turn it creates the induced EMF in the secondary. By this way I can get the secondary voltage the secondary side. So by means of the mutual induction, so this flux is linked with this coil. By mutually induct with this coil, I can get the voltage by means of the rate of change of flux lines. So in order to reduce the magnetic losses here, here I am place the core in a laminated sheets by means of the laminated steel sheets. Okay, so in order to reduce the hysteresis and the adherence. So what is that? We will see one by one. Then here this is the general EMF equation. So if I am placing the coil in a AC circuit, this is the general EMF equation. Why we need this EMF equation actually? Suppose I am using the coil in a supply or at the secondary, I have to get the voltage. So what amount of voltage I can get? That I don't know. So in order to knowing this equation, I can measure if I wound this kind of turns, what amount of voltage I can get at the output. That I can see. How? Here we can see the E is equal to 4.44 Fn pi. So here F is nothing but the frequency of the supply I given, and here this N is the number of turns. So this EMF is directly proportional to flux lines and the frequency, and mainly in the number of turns. So flux lines based on the supply only, input supply only. The frequency are also based on the supply only, but I can change the number of turns value. So if we increase the number of turns, in turn I can increase the voltage value. So at the secondary level, if we increase the number of conductors, I can get more voltage. If we decrease the number of conductors, I can get the less amount of voltage. So here I am describing each and every term. So where the E is the induced EMF and F is the supply frequency, and N is the number of turns of the transformer winding, and pi is the flux lines, magnetic flux lines. Then voltage transformation ratio. So V2 by V1 or N2 by N. So in which way I can transfer the voltage? Sometimes I have to reduce the 230 volt into 115. So 1 is to 2. 1 is to 2. The whole amount is reduced by the half of the value, and 1 is to 2 I can use. That is the voltage transformation ratio. In which level I have to increase or decrease the voltage value. That is the voltage transformation ratio. In the formula term, I can write V1 by V2, N1 by N2. And the type of level, earlier I said that we are having the step up transformer and the step down transformer. Then the type of transformers. So mainly we are having the power transformers, distribution transformers, instruments transformers, and the special transformers. So normally we already discussed that the transformer is only to step up or step down the value. Then what is the purpose of these types? Power transformers, distribution transformers, instrument transformers, and the special transformers. Power transformers, where I can use this power transformer means in the substation level, where we are maintaining the high amount of voltage. I can use this power transformer. It is like a room size transformer. The size of the transformer is somewhat high to maintain the substation level voltages. In the substation level, we are having 660 volt, 110 volt, or 220 kilovolt, 120 kilovolt, like that. The input voltage of the transformer, I can say. The input voltage of the transformer may be 66 kilovolt, 120 kilovolt, 220 kilovolt, 330 kilovolt, like that. So in order to capable that voltage, previously I shown one diagram here. So this is the example for this power transformer. This is the diagram for the power transformer. So we are having the oil tank, the cooling pins. So these are the insulators to capable that much amount of voltage, some 66 kV, 220 kV, 120 kV, like that. For that, this much level of insulation is needed. So this is diagram for the power transformers. So this power transformer is mainly used in the substation level, not for the consumer side. So it needs the weekly maintenance or monthly maintenance or daily maintenance based on the things we are considering. Here we are having the oil level gauge, temperature gauge, pressure gauge, like that. So based on that, if the maintenance is needed, means we we have to do then and then. So this is the power transformer diagram. Then the distribution transformer. So in here I am giving for the power transformer. This is mainly used in the generating stations and operate under the full load condition, and it should give the high efficiency value. So it works under the high efficiency value. Then only we can use these devices at the substation level. And this is the diagram for the distribution transformer. This transformer we can often see in our roadside. This maintains some 11 kilovolt input to the 440 volt output. So 11 kilovolt 3 phase 11 kilovolt input to 440 volt output. So from the substation, the higher level voltage is reduced to 11 kilovolt. So to 210 kV, 110 kV, 330 kV, like that voltages are reduced to 11 kilovolt. That 11 kilovolt further transmitted to consumer level. From the consumer level, we can use the 11 kV directly. We have to convert to the 440 volt 3C 3 phase AC supply. For that we are using the distribution transformer. So this is the distribution transformer. So this is used near the consumers and operates under variable load. So in the transformer we are connecting loads, not a constant one, it is the variable one. So if the new connections applied by the consumer, that connections also is given to that particular roadside transformers, and it maintains the low iron losses. Then instrument transformers. So transformer mainly is for what I previously said is step up or step down values. Here we are also using the instrument purpose also. Suppose I want to measure the 110 kilovolt supply or 210 kilovolt supply, 330 kilovolt supply, some kilovolt range. Normally our voltmeter measures some 440 volt, 600 volt, like that. Beyond that level, the size of the instrument may increase. In order to measure the value of 210 kilovolt directly means, or 110 kilovolt directly means, the size of the instruments may get increases. So in order to avoid that one, we are using the transformers. So what is actually the transformer? It maintains the voltage level. What is the primary voltage it gets, and accordingly the secondary voltage is we can get at the output. So if I am giving the 230 voltage supply, suppose the primary voltage of the transformer is 230 volt and the secondary voltage of the transformer is 150 volt, 115 volt, means if I reduce the 230 volt into 200 volt, then the 115 automatically reduced to 100 volt. Like that, the proportionally I can get the voltages from primary to the secondary level. So based on that, the higher end voltage is connected to the primary. In turn, I can measure the lower end voltage. If the lower end voltage is high, means the higher end voltage is also high value. If the lower end voltage is low, means the higher end voltage also gets low value. Like that, I can measure the voltage level, high level voltages by means of this instrument transformer. So here we are using the current transformers and the potential transformers. So my ultimate aim is to maintain the power value. So what is the power actually I am getting? What is the power of the system? For that we need the current value and also the voltage value. Then only I can measure the power value. So in order to measure the current value, online the conductor I am placing one transformer. So on the conductor we are having the flux lines. That flux is linked to this secondary of the transformer. Accordingly it gives the value. Based on that value I can measure what amount of current is flowing through this conductor. And for the potential transformer, like that, the primary winding is some value, means correspondingly the secondary winding is also the proportionate value, having the proportionate values. Like that, the instrument transformers are working in the power system in order to measuring purpose, measuring the voltage levels, current levels and power levels. Then what are the losses in the transformer? So each and every device having its own characteristics. So if I pass the current in the coil and it gets the magnetic property. So when I pass the current to the coil, it gets the magnetization property. So consider, for example, see, this is actually the transformer. So in the transformer I am giving the supply. What will happen if I am giving the supply? The magnetic flux lines are created each and every turn of the coil. Each and every turn of the coil. So cumulatively I can get the magnetic flux lines like this. In the diagram, for the simplicity, I draw the narrow line from the secondary, primary to the secondary. But practically it is not happening. Practically it is not happening. So flux is chosen the path where it can go. So it can go in anywhere. It is like a air. Magnetic flux lines is like a air. It may have the path in anywhere in the any direction. So magnetic flux lines are in this direction, right direction, left direction, up and down, like that. So we can get the narrow magnetic flux value to link to the secondary set. So we can get the narrow line linked to the secondary set. Some fluxes are wastage. That is not the useful flow. That flux is called useless flux. So by means of that useless flux, suppose that flux is linked some nearby iron conductor or copper conductor, means that itself creates some voltage value or current value. So first of all, it induces the voltage. If the closed path is there in the conductor, means the current is also flowing. That is called eddy current. So that is the wastage of current. That current is absolutely waste one. So the eddy current is wasted. That's why we can call it as a eddy current loss. If the current is wasted in a resistive material means, or any kind of material means, so all kind of material having its own resistance value. So current flowing through that material, suppose it has the resistance value, I can say that that is I square R loss value. So without the usage of the current is creating or flowing to the resistive material, and it creates the losses. That losses is called eddy current losses. And what sometimes I can say some hysteresis losses occurs. What will happen? And each and every time I changing the direction of fluxes, because the nature of the alternating current, each and every time it changes its direction. So if the current flowing through the conductor direction changes, means the flux polarity also gets changed, the magnetic field polarity also gets changed. So due to the magnetic field polarity changes, at that time some energy is losses by means of heat. That heat is called hysteresis loss. Mainly due to the reversal of flux lines in the magnetic medium. Reversal of flux lines in the magnetic medium. That loss is by means of the heat. That heat is called hysteresis losses. So that whenever we consider the magnetic effect in the as a phenomena in the principle, we have to consider the losses also. So that hysteresis loss and the eddy current loss is come under the core loss section. Here we are mentioning the core loss in the secondary side. Here we are having the core. So that's why I am mentioning the core loss is further divided into hysteresis loss as well as the eddy current losses. Okay. So for the copper loss, mainly due to the conductor we are using. So in the transformer, what are the how many conductors we are using? We are having the primary number of turns as well as the secondary number of turns. So in the primary number of turns, we are having the number of turns of the coil and as well as the secondary side also. So if I am having the copper conductor and the current is flowing through the copper conductor, means the conductor itself having its own resistive property. The conductor itself having its own resistive property. Because if any object having its own length and cross-sectional area, it has the resistive property. It has the resistive. So if the resistive property is there and also the current is flowing through that material, means I can directly say that there is some losses. If it is the copper material, I can say that that is the copper loss. That is the copper loss. So that's why in the losses in the transformer, I can refer the copper losses, core losses, hysteresis losses and the eddy current loss. So the hysteresis loss and eddy current losses come under core losses. Then the efficiency of the transformer. So if I consider any device, we should monitor what will be the efficiency. If I use the device, if I want to use the device, I have to measure what will be the efficiency of that particular device. So here also we have to consider the efficiency of the transformer. So in general, the efficiency of the transformer is nothing but the output by the input value. Here I am giving the input and I am getting the output value. So here I am giving the input value actually from the primary side. So primary side we are having the voltage value and also the current value. So I can, that is the input power. But what will happen? Previously I said that some leakage of flux is there and also the magnetic reversal also is there. So due to the magnetic reversal, one heat energy is wasted, and due to the leakage of flux, some unwanted current is producing, that also creating some losses. So that two losses occur in the transformer core side. And on the conductor side, we are having the copper loss, I square R. In general, I am saying that is a I square R losses. So that loss. So input is getting some losses and the output I can get at the secondary side. Here I am transferring the energy only. Here I am transferring the energy only. So that's why here I am mentioning efficiency is equal to output by input. So in order to put the input, here I am mentioning that is the output plus losses. Output is nothing but input minus losses. That's why input is equal to output plus losses. That's why here I am mentioning output by output plus losses. So this is the efficiency of the transformer. So this is the main parameter while we are considering to use the transformers wherever we need. Then what are the cooling methods we are adopting for the transformers? So earlier I said we are having the transformer oil tank in order to coolant the winding. So if I pass a huge amount of current in the conductor, it heavily heated up. So the heat should be transferred to the atmosphere. For that we are using the transformer oil. So even though I am using the transformer oil as a cooling medium, beyond some level the conductor is heated up, means the transformer oil also get heated up. I have to coolant the transformer oil as well as the winding. So periodically it will be monitored by means of some gauge meters. So temperature gauge, pressure gauge, or winding temperature, or oil temperature gauge, like that. So based on that, what will be the cooling level that we can monitor. In order to coolant that oil, we can use the air natural method. So some cooling fins are here, see in this diagram. Here we are using the cooling fins. So this oil is heated up, means automatically it try to circulate. So the circulation by means of the cooling fins means small pathway. It is the small pathway. Then the atmospheric air strikes on the cooling fins. Then automatically the heat is transferred from oil to the atmosphere. Then the circulation continues until the temperature level is reduced to the desired value. Then sometimes in order to use the air cooling method, we are using the oil cooling method. That is, we are already mentioned. So the transformer is immersed in the oil tank. Immersed in the oil tank. That is the oil natural method. Sometimes the heat is huge amount, means the forced oil strikes on the conductor. The forced oil strikes on the conductor. That method is also used under the cooling methods. Then we should have the testing of the transformer. So suppose I am using the transformer year and year. Then what is the whether the characteristics of the transformer is changed or maintained its own, that I have to know. For that, the testing is very important for any devices. So how the transformer is tested? By means of the two things, by means of the open circuit test and by means of the short circuit test. So without conducting the load, I can measure what will what will be the efficiency. If I load the transformer, what will be the efficiency? I can find by means of these two tests. So I can predetermine the efficiency value, not actually conducting the loaded test. For that I need the open circuit test and the short circuit test. So in the open circuit test, what I have to do? Normally I give the voltage on the secondary side. So suppose I am considering the step down transformer. In the step down transformer, here I am having secondary turns is for, first of all, I have to clarify the step up or step down transformer, how the voltage level gets reduced. So normally primary turns is 30, secondary turns is 50, means that is step up transformer. Normally primary turns 30, secondary side is 15, means it is a step down transformer. So if the number of turns is reduced, means it is a step down transformer. The number of turns increases, means it is a step up transformer. So in the open circuit test, I am giving the supply where I am having the more number of turns. Not even mention the primary or secondary. That is not a matter. I have to give the supply where I am having the more number of turns. Then the other end is measured, open circuit. I'm not connecting any load. I'm not connecting anything. I got to only measure the voltage value. In the primary side, I am measuring the voltage value, current value as well as the power value. So for the open circuit test, I have to open the more number of coil side, and for the short circuit test, I have to shorten the less number of coil side. Okay, so keep in mind, when I am conducting the open circuit, you should open the more number of turns coil. You have to give the supply in the less number of turns coil. Okay, suppose we are considering the step down transformer. Consider one step down transformer means in the secondary side only you have to give the supply when we are conducting the open circuit test, and at the primary side you have to measure the voltage value. And on the short circuit test, we have to shorten the secondary side of the transformer, and you have to give the supply some 30% of the supply. That is the main thing. 30% of the supply only you have to give in the transformer primary side. So based on that, you have to measure the short circuit current value. Based on these two test readings, I can predetermine the efficiency value of the transformer. What will be the voltage regulation and what will be the efficiency for each and every current I assume. Each and every current I assume. That is the testing of transformers. Then what are the applications we are having? Normally in the transformer is mainly used in the power systems, industries and electronic sites and the renewable energy sites. So normally the renewable energy is more compete in the real-time scenario. So in the wind farm we are generating some voltage, and I have to transfer the voltage level into that usable level. For that we need the transformers. And for the electronics side, mainly it is used for the isolation purpose. Some high voltage level to the low voltage level. Some low voltage level circuit is also there. Some high voltage level circuit are also there. So in order to isolate these things, we need the transformers in the electronics side. Okay, and also like that for industry and the power systems also. What are the advantages it has actually? Mainly it has the high efficiency value. High efficiency value, especially no moving part. So the friction losses, or wherever we consider the mechanical losses, that is not happening in this device, since it is the static AC devices. Then long service life. So it doesn't have any frictions. Normally it has its own life for the long time period. That is the main advantages of this kind of devices. So even though it has some advantages, it has the limitations also. So works only with AC. Why? This is works under the principle of mutual induction only. For that mutual induction purpose, we need the flux changes value. So the flux changes value occurs only by means of the AC supply only. Suppose I am connecting this transformer in the DC, nothing happens in the secondary side. Even though I am giving the supply to the primary side, if I am giving a DC supply to the primary side, in the secondary side I can't get any value, since there is no rate of change of flux in that particular coil and not links with that other coil. Then heavy and bulky. So for the low current rating also, the weight of the winding is also get more, and high initial cost. So in order to erect this one, we have to give some high initial cost, spend high initial cost. That is the main limitations of this kind of tips. Even though it is very, very important, these are some limitations is there. Then up to now, here we are studying the principle of operation. What is the principle actually? By means of the mutual induction principle. Then what construction is? So mainly it has the primary, secondary winding, transformer core, oil, then oil tank, then conservator, then bushings for the insulator and the breakers, like that. Then we are having the types: core type transformer, shell type transformer and the berry type transformers, like that. Then we are considering the losses and the efficiency. Losses, we are having the core losses and copper losses. So in the core loss we are having the hysteresis loss as well as eddy current loss, and in the efficiency we are considering what, in which way it will work proper, and the application where it is used, like that we are seeing. So thank you very much for listening.